Hey everyone. All right, so this is another video that is really dedicated more to a math concept than a physics concept, but it's a math concept that is super foundational in physics, and so I want to make sure that everybody understands it as much as they need to. So we're going to talk today about vectors, what they are, and then we're going to do some vector decomposition and recomposition, and talk a little bit also about notation. So in physics in particular, like I know a lot of people can often think that physics feels like another math class, right? But there are some really unique things to physics that you don't always learn in other math classes. So, for example, like units. Some math classes just don't really deal with units, and that's because they are really more focused on the numbers themselves. But like obviously, if we're going to be doing math with actual physical quantities, we need to know, are we talking about meters or centimeters or inches or feet? And so similarly, vectors are one of those areas of math that a lot of times we don't get to until we need to do a physical application. So if we think about certain physical things that we measure, we often have some where just a number is enough. So a good example of this is like how much you weigh, right? You might say 100 pounds. Or another example could be cool. We're cutting that part. These are called scalars. And they are measurements where only the number is needed. However, in physics, there are a lot of measurements we make where we need not only a number, so measurements with a number and a direction. And you can think here about like from Despicable Me, like vector, he has a magnitude and a direction, number and direction. Good physics joke. We call these vectors. So a vector is simply any measurement we take where we need to have not just the size of the measurement, but also the direction of the measurement. And so this is forces, this is velocities and accelerations. And honestly, a lot of what we measure in physics is vectors. Now, when we're dealing with direction, how we deal with direction is really interesting. And so there's a couple of ways that we can notate vectors, that we can talk about vectors. So kind of the simplest, and this is the one that we use a lot in like an algebra-based physics class, is just some sort of notation about the angle that it's pointing in. So you might say something is moving at 20 meters per second at 20 degrees north of east. And that would just mean that it's at 20 meters per second and that the angle it makes here is 20 degrees, right? So we've gone 20 degrees north from due east. This is a really, really common way to talk about vectors. However, we also can use what we call component notation. And this can be very handy, especially when we start to get into more complex math with our vectors. But to understand component notation, first we need to talk a little bit about vector decomposition. So let's take this vector over here. If I look at this vector, I notice that when I move this 20 meters per second north of east, what that means is that each second I'm moving some amount east and some amount north. And we would call these the X and Y, or like horizontal and vertical components of that vector. Now, if you see this, you might start getting some flashbacks to right triangle trigonometry from geometry, because that is absolutely how we solve these. So if we wanted to know what the X and Y components are here, we would use the sine and cosine, because the sine of 20 degrees, so katoa, right, is the opposite edge divided by the hypotenuse. And the cosine of 20 degrees is, so katoa, adjacent edge divided by the hypotenuse. And so with a little handy unit circle, or in this case, more likely calculator work, we would have y is 20 sine 20, which is 6.84. And x is 20 cosine 20, which is 18.8. So what that means is that each second I'm moving 6.84 meters per second, meters vertically, and each second I'm traveling 18.8 meters horizontally. And these are what we would call, again, our horizontal and vertical components of that vector. So something that I think is important for people to see is that the total 20 is not equal to the two components added together. Instead, it's actually using the Pythagorean theorem with these two will get you this third. All right. And that's just because vectors don't add the same way. We're not adding two things in a straight line. We're adding them left and up, or right and up in this case. And therefore, the distance here, which is really what we would be looking for, is not simply adding those two together. Now, if they were in the same direction, right, then the distance from where we started to where we ended would be adding them, but they're not. All right, this lets us now talk a little bit about what we would call component notation or unit vector notation, or there's a lot of different ways to talk about this. So instead of describing this in this way, as 20 meters per second north at 20 degrees north of east, we could also write this velocity as 18.8 I hat plus 6.84 j hat. Now let's talk a little bit about what that means. I hat and j hat. In math, we basically have three unit vectors, which are one unit length, and they're in the x, y, and z directions, and we call them I hat, j hat, and k hat. And then what we're doing here is just lengthening it, right, by multiplying it by this amount. So what I am saying in this is each second I'm moving 18.8 in the x direction and 6.84 in the y direction. And so that's a really common way of looking at the notation. Sometimes we actually like drop the I hats and j hats entirely, and we might write it in like more of a matrix vector notation. Something like this. That is fairly common in engineering school. It's fairly uncommon for the AP Physics test. The AP Physics test will not ever really require that you write something in this way. You will always be permitted to write it in that way, but sometimes you'll find some of the math a little bit easier if you do. And certainly like adding different components together becomes easier if you do. So in fact, let's think about that problem. Let's say we have two vectors. We're going to call them vector A and vector B. And if I want to add them together to get some resultant vector, what do I get? Well, the best way to do this is actually to break it down into that component notation, right? So A and B each have horizontal and vertical components. So for instance, and I'm just going to use some numbers here. Let's say that A is 5 I hat plus 3 j hat. So that would mean that these are like 5 and 3. And that B is -1 I hat and 5 j hat. So if I want to know what A plus B is, and I have them in this notation, it is suddenly really, really easy because all I need to do is add each component. And I end up with 4 I hat plus 8 j hat, which would end up being something like that. Call that C. Subtraction works the same way. Now, something that does not work the same when we're working with vectors is multiplication. And it turns out that there are actually basically two ways for us to multiply vectors together, which are dot products and cross products. And so my next video, I'm going to try to tackle that. What is a dot product? What is a cross product? When do I use each? And what are some of the main physical applications there? Cool. Thank you. Bye.